So welcome to this presentation on the Digital Futures project entitled PERCy Perceptive Cellular Networks for Road Transport. This project is a cooperation between the KTH Embedded Control Systems Department, KTH School of Electrical Engineering and Computer Systems, Scania, and Ericsson Research. Now, please meet our project team, Professor Turngren, Professor Skoglund from KTH, postdoc researcher Dr. Sajjad Dai-Omshi, and doctoral student Gianfilippo Fornaro at KTH, Ulrich Janusson, Scania, Stefano Sorrentino, and myself, Gabor, further presenting at Ericsson Research. So now let us start by asking the question what a perceptive dependable cellular network is and why we need it. But the key observation that we are making in this project is that safety-critical road transport applications, such as advanced driver assistance systems, require safety analysis and safety certification, in fact. Now, road safety is greatly enhanced by enabling cooperative awareness among road users, such as drivers and pedestrians, for example. And cooperative awareness, in turn, is facilitated by a perceptive cellular network. That is a network that provides both communication and radar sensing services, that is, intelligently perceives its environment and communicates that perception to the road users. And the technology that enables such networks is called integrated sensing and communication, ISEC systems. So the key idea of the PERCy project is that we should enable cooperative awareness among road users and share that information among road users by letting cellular networks to sense, apart from providing high-quality communication services such as mobile broadband services. Now, it follows intuitively that the system model for PERCy, that is for the perceptive cellular network, must incorporate passive objects, that is the targets for radar detection and sensing, and nodes that transmit signals for both communication and sensing purposes. Our system model and concept must also include intended communication receivers, because we would like to maintain high quality communication, quality of service for communication purposes like mobile broadband services, as well as receiver nodes for the sensing signals, that are the nodes that are receiving and analyzing the radar signals, and scatterers that constitute the wireless propagation environment. So this picture on the right-hand side illustrates a cellular system in which the cellular base station serves as a transmitter, and it also can serve as a sensing receiver, since it has sufficient antenna and radio resources to both transmit and receive and analyze signals. While in this example, a user equipment device on the right-hand side is the intended communication receiver. Now, it makes sense that since we are talking about an integrated sensing and communication system, an ISEC system, we somehow need to household and share resources between sensing and communication purposes. And without going too much into the details, we in this project developed the concept of a concurrent mode operation in which communication and sensing take place simultaneously in time and frequency using the spatial resources ensured by our antenna systems. Or alternatively, it can operate in time division mode in which sensing and communication is taking place one at a time. Now, in the next slides presented by Sajjad, we are going to look a bit more at the technology details, that is, what is under the hood of an ISEC system.
Hello, my name is Sajjad. I will continue Gabor's presentation by introducing three different topics that we're currently working in PERCy project. The first item is optimal resource allocation in time-varying ISEC systems. We consider a base station with several targets considered to be vehicles and a number of mobile communication users. Resource allocation in time-varying ISEC systems is divided into two parts: acquisition mode and tracking mode. In the acquisition mode, we need to design a single waveform for both communication and radar tasks in order to efficiently use common resources. In the first step, without having any knowledge of the environment, the base station sends downlink pilots towards both targets and communication users. Then communication users estimate their own channels and send it back with the uplink payload towards the base station. There is a guard period between the uplink and downlink payload in which the base station receives the echoes of targets and communication scatters. The base station is now able to distinguish which part of the echoes are related to communication scatterers and which part to targets. Then we have downlink data communication and also uplink data communication. In the tracking mode, we obtain the communication channel based on the correlation structure of the communication channel, and we track the targets based on geometric characteristics of targets, which can be vehicles in vehicular networks. Intuitively, in order to save resources, it would be better not to send downlink and uplink payloads more often. The question that arises is how often we should update our knowledge about communication channel and target parameters. Answering to this question is equivalent to solving a multi-objective optimization problem, which leads to optimally allocating resources. Some of the objectives of this optimization problem can be maximizing downlink data rate, maximizing uplink data rate, minimizing chimeral bound of target parameters, or minimizing a statistical dimension with prior information. Our next focus is on the second topic, blind sensing and communication. In this domain, we examine the challenges posed by an ISAC receiver tasked with simultaneously receiving uplink communication data and target echoes. The coexistence of communication and radar signals in the same frequency band can lead to mutual interference, potentially introducing errors in both communication data and radar operations. For instance, this interference could result in autonomous vehicles making inaccurate decisions, which could pose significant risks to public safety. The primary objective of this project is to differentiate and distinguish target echoes from communication messages within the shared common ISAC receiver. This goal is achieved through the design of suitable modulation schemes and the coordinations between users and base station, enabling the recovery of communication messages and the detection of target parameters without the reliance on pilot signals. This approach of not using pilot signals can significantly save resources in ISAC systems. Moreover, in scenarios characterized by highly dynamic targets or communication channels where there is no prior knowledge regarding the aging of the communication channel over time or the geometric properties of unknown targets, the initial acquisition step of ISAC may be prone to significant errors. The focus of the last topic we are considering within PERCy project is on wireless connectivity and perception challenges. Wireless connectivity and sensing is the backbone of future digitalization. The number of IoT devices with sensing and communication capabilities is explosively growing in the near future. Consider the depicted vehicle highlighted in red, which has both sensing and communication functionalities. Now let's direct our attention to the two images on the slides. The minimum amount of resources that is required for both sensing and communications in the intended vehicle is much larger in the lower image than the upper image. What is the difference between these two images? The key distinction lies in the considerably higher number of inactive devices within the network in the lower image. This is indeed the biggest challenge of massive connectivity and comprehensive sensing. What does it mean actually? It implies that even with the best existing schemes in communications and radar technology, the number of objects surrounding the intended vehicle that can be detected is inversely proportional to the number of inactive devices in the whole network. Consequently, the current state of ISAC systems cannot feasibly offer connectivity for a large number of devices, nor can it deliver comprehensive sensing capabilities. As a groundbreaking initial step, we have devised a solution to address the formidable challenge of massive connectivity, and notably, this solution operates independently of the total number of inactive devices. Moreover, we are actively engaged in the development of a methodology to resolve the issues associated with the massive sensing and connectivity. This endeavor has the potential to unlock new horizons in the domain of wireless connectivity and sensing. Here are the references, including the related published IEEE papers and ongoing works. Thank you very much for your attention.